Okay, so hello and welcome. So today we are going to discuss about the unification of momentum and energy in special theory of relativity. So we have already derived the expression for momentum and energy in the theory, and the momentum was m times gamma u, and not just nu, and the energy was n gamma c square, base of course for a free particle, right? So I'm gamma c square, where it is not just half mv square. So that's what we have seen in special relativity. But now what we're more interested in is just like four vector of velocity, which we have defined some earlier. We have defined something like dxi by ds, right? So we are interested in finding whether we can actually find something like a four vector of momentum. So a momentum four vector we are after momentum four vector. Why we want to create these four vectors? Because in the four vector formalism actually takes care of the time also as a shape, also as a dimension. So basically, in special relativity, because time is a dimension, so the vectors has to be of the dimension 4 and not 3. So they should not be ordinary 3D vectors. So if you want to understand relativity, we really have to construct the required four-dimensional vectors. So that's why we are after them. And there is one thing that is associated with the four vectors is that whenever there is a four vector, you can create a invariant quantity out of it, and that invariant quantity is is something which has some information about the geometry, about the intrinsic geometry of the space-time. So the invariant quantities associated with the four vectors have a real geometrical interpretation in terms of geometry or topology, which topology I think I will not be able to discuss because I don't know much about topology myself. I still have to learn that, right? But I do know this factor that any invariant quantity in tensor analysis, if you have, then that does have a geometrical interpretation from the, of course, the geometric point of view. Okay. So enough about words. Now let us see how we can construct a four vector momentum four vector. So let us just see the outline without even deriving. So if there is a momentum four vector, so the momentum four vector should be of the form something like P0, P1, P2, and P3, right? Where these upper indices, they are not powers, rather they are this is the contravariant momentum four vector, right? And we can as well represent them in the covariant form. There is nothing special about the contravariant form. This one is the covariant momentum four vector. The naming of contra and co, so it's just like how the basis vector transforms. So co means here that if a quantity, if a four vector, they transform exactly like the basis vector, when the coordinate transforms, then it is a covariant four vector, and if it transforms opposite to that of the basis vector, then it is a contravariant. So I mean, it's very easy to see, and you can check it out or prove it to yourself how basis vector transform the coordinate transformations. Nothing very technical here. Okay. So for our purposes, it's enough to just remember that contravariant means upper indices and covariant means lower indices. That's all. That's all. That will suffice for our purpose here. So let us see. So from here, one thing that we know already from the, because the signature of the metric that we have, the Minkowski metric. So in case I did mention earlier, the Minkowski metric. The Minkowski metric is something of the form, like in matrix form, it can be written as minus 1, 1, 1, 1. This is what the signature, sorry, my bad. This is what the signature that Landau has considered in the book, so we'll follow that. So this is Minkowski metric, and in general, if you have a metric tensor, it is a form of a metric tensor. Basically, it is a metric tensor. I hope you have proved that it is a tensor. I have not proved it, but you should prove it yourself. Okay, because then that would be too mathematical to go. If we prove everything in one course, it is not good. Okay, so much of the talks now. So basically, what I wanted to tell is we can write the P1, sorry, P0, P1, P2, P3 is equal to P0, oh sorry, my bad. This should be here because we are writing covariant. So P0, so P down 0, so contra variant P0 or covariant P0, they are same because plus 1 is here, right? And other are just negative versions, something like this. So time component is same, but the space component are reversed by the sign. And you already know how to lower and upper the indices. So the trick is that we write this as eta ij and pj. Okay. Now there is a summation on j, right? And now you can convince yourself that indeed this is the case here. Okay. So now let us first let's just talk about how we can get how can we define momentum from actions, because see, we are deriving everything from the action and Lagrangian, right? And even Lagrange, we have derived the Lagrangian from the action only. So the action is the basic thing that we are after. So we want to derive the momentum for vector also from the action, and we can do that. So the action S is what we were doing. It was alpha integral ds from a to b. This was our action, relativistic action. Alpha, we proved it to be minus mc. If you do not know this, just watch the older videos. So this is our action, and now what we can do is we can define the 3D vectors. We can define the three-dimensional momentum vectors as something like del S over del R. So this is the momentum vector. Now, if you ask the proof for this, you have to look the Landau-Lifshitz volume 1 on mechanics. The proof is fairly simple. Okay. It's very simple. You just have to take the variation here and then take the variation in the Lagrangian, do some product rule tricks, and then you will get this form. So Landau lecture volume 1 on mechanics, you will be able to prove that. So, but this is for 3D, because there we know that it happens to be for the 3D vector. Now, what about the time component? What about, so this would give you the three-dimensional momentum vector. Okay, so the momentum 4 vector, basically, if we see, so the momentum 4 vector has these components, uh, P1, P2, P3. So momentum 4 vector has P0 and P vector in short. So you have achieved the P vector by directly taking the partial derivative of the R, right? If we are able to compute the partial. So still we have to actually we have to compute the LHS in order to get the P, right? So we have to do this calculation here based on the specific form of the DS that we choose in the special relativity. So we have to solve for the P vector, but in principle, once we do that, we have to solve the problem for determining the P vector here, right? Now the problem remains for the P0. So how to find this time component, right? So how to find time component? So again, here, because we are defining the action such that we have the dimensions are 4. So we are defining in 4 dimensions, right? And here del S by del R vector is just for 3 dimensions. So what we are doing here is just simply extending the dimension, and we can write that if we take time also as a dimension, we can write del S by C dt. Oh my god, del S by C dt is just should be equal to P0, right? Because here the R vector is just our ordinary three-dimensional space. And now if we take time also as a dimension, then we should be able to write the zeroth component of the momentum as P0 and del S by CDT. And we know that this should also be, so we also know that P0, 0, it doesn't matter here. So it just, they are all same. So if we are able to calculate this quantity here, del S by CDT, and del S by del R, we are good to go basically. So we know everything. We will be able to compute the momentum for vector, right? Now let's jump on to calculate the partial derivatives of the S. Let's calculate the variation of action S with respect to coordinate. So we just have to calculate now the variation of the action S with respect to coordinates, because that's what we need. We need to compute the variation of S with respect to the coordinates, because here time is also coordinate and this one here, right? So now we remember that the action was equal to alpha A to B ds, which I have written here, and alpha we remember as minus MC, right? But what was ds? So this question we asked, like what was actually ds? So alpha A to B ds was simply eta ij dxi dxj. I don't think there should be any problem. If you have a problem with what these terms are doing, I think you should watch my old videos or watch other YouTubers' videos, which are very well illustrated than me. But this is simply the invariant ds square root, which was c square dt square minus dx square minus dy square minus dz square. So the invariant space-time interval, that is the ds. I'm just writing in it a more, I will not say fancy form, but in a more general form, and easy to do algebra form, basically. So eta is a, you know, and dxi dxj also you know, so it's fine. And also here the I and j, they go from 0 until 3. So that is very important to remember, because we are dealing with the four-dimensional space-time, and this I and j are in the sum, which is the Einstein summation convention. Okay, so now what is delta S? So delta S should be a 1 upon 2 root eta ij dxi dxj. Now, one thing you should be able to see is that the eta ij is just a constant metric. So it has plus ones and minus ones here. So it should not, like, it is a constant basically. So it should not be, it will not vary basically. So the thing here is that we have eta ij, and then we have something like delta of dxi and dxj plus dxi delta of dxj. Okay. Now from this metric thing, you also realize that this metric is a symmetric matrix, and its symmetricity is what, uh, symmetric metric. So its symmetricity we'll exploit now. So we know that eta ij is equal to eta ji. So using this, what we can write is, we just expand the numerator in two terms. So it would be alpha by 2 integral, and notice the bottom term, it is just ds. So very nice, and it will be two terms here. So eta ij delta dxi dxj, and plus eta ij take dxi delta dxj. Now what I am arguing here is, what I am claiming is that these two terms, if you look closely, they are same. Why they are same? Because if you just swap the indices I and j, they will be the same. And if the swapping doesn't change the metric tensor, the Minkowski metric is symmetric. every metric is symmetric. That is also something to be proven, but let's just leave that here. So the thing is that these two terms are same. So they are just two times of the first term we can write. So 2 will cancel. So it would be simply alpha from A to B, from A to B, and it will be something, uh, let's write it, eta ij delta dxi dxj divided by ds. Okay, so we have reached this stage. Now, what we can do from here is that we can eliminate this. I mean, not eliminate. We can just substitute this eta ij very smartly by putting this eta ij inside this delta thing. So it would be alpha a to b. It can be written as eta ij dxi and then dxj divided by ds, right? Uh, mm, See there, we can either do two things. Either we can lower the index of this dx, or we can lower the index of this dx. That's what I'm interested in. So I think in the book we are lowering the index of the this one here. This, so just do that alpha a to b. So try to look at it at this expression multiplied by delta dxi by ds, right? Now the expression in the bracket, it is just lowering the indices. It will be just dxi, where I is in the subscript, so it will be dxi here and ds, right? And then here it is. This one we can write basically delta of d of delta dxi. Now identify this thing here, dxi subscript by ds. This is nothing but the covariant velocity for vector. So we can write it as ui and then d of delta dxi. Now we can apply the by part integration. So we can write it as alpha. Let us leave alpha outside. So alpha, when this integrates over, only delta dxi remains, and boundary values a to b minus whole integral. We take the derivative of u to s, and then integrate this delta dxi, and then the total integration. So this is the simple by part integral here. Now we see that this should be equal to delta s. Okay. Now the whether the delta s will be 0 or non-zero, it depends on what? It depends whether, first of all, we have to choose the variance of coordinates. So very important thing, variance of coordinates here. So let's say we are having from A to B, right? Now if we vary B, so if we fix the B, then delta of xi at B is equal to 0 and delta of xi at A equal to 0. If we fix the both the points, right? So if we fix here both the points, what we'll get? We'll simply get, we should get actually. So the first term is 0 and delta s would be, so for fix. So let's make the cases. So case 1, B is fixed, and obviously A is also fixed. So when B is fixed, we get delta S is equal to this thing in this integral A to B du I by ds, and delta dxi d is S for a fixed B, and the trajectories which are admissible, or the which follows the Euler-Lagrange equation. So this quantity delta S is 0, that we have seen, the stationary action principle. So for that we know that it will be only possible if dui by ds is 0 in general. So dui by ds is 0. So if that is 0, then we can write the delta S as delta S equal to alpha ui, sorry, ui delta dxi from A to B. right? Now, basically, what we are seeing in this equation is that if we vary, so if A is only fixed, so this is our case 2, A is only fixed and B varies, right? So A is fixed but B varies, but the we are still we are still tracing the trajectories which follows the Euler-Lagrange equation. So in that case, delta S is equal to alpha ui delta dxi. And I think that this delta should not be there because we've integrated over. So this one here should be only delta xi. Like that. Mm, yeah, here it is fine. Here it's fine. Completely fine. But here again, this D should not be there, and here also. That's So when B varies, the delta S varies accordingly. So the action varies because the final point we have not fixed. If we have fixed the final point, we know uh, where the trajectory is going to end. Then we know that action should be stationary. But the action will vary if we do not fix the final point. If we keep on varying the coordinate, the action will vary. And this coordinate also has the time itself as a coordinate to set. That should be remembered. So here it is very important to remember that I goes from 0 to 3 and not from 1 to 3 in the case of that was the case of the non-relativistic classical mechanics. Okay, so we have derived this results. Now from here we can see that basically del S over del R, which is the momentum 3D vector, and it is equal to alpha ui. But notice one thing, a very peculiar thing here. Uh, this ui in the denominator is a covariant velocity vector. Okay, so writing in this form is it will be very confusing. So what we can do is we can simply write ui, or rather alpha ui is equal to del s over del xi. Remember, the xi's are just coordinates and ui is the velocity 4 vector components for I from 0 to 3, right? So that is very important to remember, which corresponds to, as we have seen, the results from the classical mechanics. So let us go back. Why we are doing these things here? Because we know something like this. So del S over del R is equal to P vector. And we have seen del S over CDT is equal to P0. So just generalizing this expression, we can write. So what we can do, we know that, let me write it again, del S over del R is P, right? 3D, and P0 is simply del S over CDT. So this thing we know, and what we can see from here is that P del S over del R, when we are writing this P vector here. So one thing that we should really see is that these P vectors are ordinary 3D vectors, right? These P vectors, ordinary 3D vector, and the ordinary 3D vector corresponds to the contravariant component, right? They really correspond to the contravariant component. So what we should do here is that we should really write from here. If we so we should really start from this expression and open each and every component. Only then it will be much clearer. Otherwise, it will all be a very bad mess. So del S over C dt is alpha times u0, right? Del S over uh, del x, right? Taken from here. Now, what it should be? It should be alpha u1, but then we know from the metric it should be minus times alpha u1, right? So there is a minus inversion when we want to do for the contravariant component. Similarly, del S over del Y is equals to minus alpha U2 and del S over del Z should be minus alpha U3, right? So this is really important. This thing is very important here. And from here we see that del S over del X. So from here, and now we can compare. Now we can compare del S over del R, del S over del X, right? And compare the just the covariant, sorry, the contravariant components. Right? So P1 is equals to minus alpha U1, right? And what was U1 exactly? So U1 was gamma by C and U, correct? And what was alpha? Alpha was equal to minus MC since starting. So just plug that in and we get P1 is equal to M gamma U. Or rather, it should be U1 here, not the whole vector. P1 is M gamma U1. So this we know already, nothing special about it, I think. M gamma U2, P3 is M gamma U3. But these are all we know already. We have derived these expressions. But what is special here is the zeroth component of the vector, right? The zeroth component. That is what we are more interested in. So just make use of this equation. So here it should be minus less over CDT from the very definition of how we are really like defining the zero vector, because in the non-relativistic mechanics there is literally no way of seeing this, but here we can see. So P0 is equal to minus less over CDT, right? And which we have here as alpha u0. This minus sign is important to negate the, so it is basically alpha, negate the effect of this alpha here. That's why we are defining it with minus sign. So P0 is MC, right? And u0, what was u0? So u0 was simply gamma, if you remember, right? But there is something special about this expression. The special thing about the zero component is that it P0 is nothing but the energy upon C. So remember, because energy was mc square gamma. So it's simply just to divide C from the energy and then you get the P0. So this is the unification, unification of energy and momentum. This is the unification. So basically now we can write the momentum 4 vector as epsilon by C and P vector, where epsilon is the energy. So this is our momentum 4 vector. Now we know from the general formalism of the 4 vector, if that is the case, then there is an invariant quantity which is Pi Pi. This is invariant. This is something which is invariant. So that you can find, and that is something like here it would be from the metric signature, it should be epsilon square by C square and minus P square. This is something that is invariant. Now your task is to just find what is invariant here. You know the expression for P vector, you know what is epsilon by C. Try to equate and try to just compute this expression, and then you will get something, something invariant quantity, and then you will get a very famous equation is that is E square is just P square C square and plus some quantity which you should compute on your own. So that is pretty much it. I think I have a little bit confused myself and the audience as well. regarding this issue with the, because here the p vector was del s over del r simply the special thing we know, but what about this negative? What about this while there is a negative sign here to really compute the things, so that I will prove in the next video for sure. Okay.